Okay, I think I have to start. New chapter. We finished 2 chapters and the exam for it. Now 17 and 18, and there will be another exam, midterm 2, right? Every 2 chapters we have an exam. So we start with the electric charges. We looked at the electric charges and force, electric force and electric field. Now we move to what happened when these charges start moving. That is when we have current. And with the current, there is another concept called resistance. So we will discuss this. This chapter is all about current and resistance. So this is the contents of this chapter. We'll start by defining what electric current is. Okay, let's check section 1. We'll have some equations that goes with that, the definition of the current and the one more equation. Then we look at the microscopic view. I mean, we go into the atomic scale and microscopically, what happens when the current is flowing, the charge is flowing. So then we look at the speed of the charges, because current is actually nothing but flow of charges, moment of charge. Section 3, we'll introduce this current and voltage measurements in circuits. Okay, current can be measured, and voltage, the potential difference between 2 points in a circuit, can be measured. Section 4, the resistance, resistivity, and something called Ohm's law. Section 5, this resistance is a quantity that we derive for current and voltage measurements. And then there is the Ohm's law that goes with that. Then we will see how this resistance varies with temperature in section 5. Then electrical energy is an energy form. When the charges move, it can carry energy with that, and that energy can be transferred to, say, if that's an electric circuit with a battery, and the energy, electrical energy from the battery can be transferred to the bulb as light energy. And the power is how fast the energy transfer is made. Then lastly, a section on superconductors. And the section 8 is omitted, that's why it is dimmed. Okay. So let's begin by defining current. Initially, at the beginning, when they found the electric charges, they knew about the electric charges, but there were not many applications on that because they didn't know how to utilize the energy. So all the practical applications are on the static electricity. But with the invention of battery, okay, this happened around 1800 by a physicist called Alessandro Volta. So that's why the name voltage comes in, or the unit for measuring the voltage is volt. That's after this physicist who is called the Alessandro Volta. So when we had this battery, which can send electric current, a steady source of electric current, then scientists start to learn how to control this flow of these electric charges in circuits. Now, what is the circuit? Circuit is where we have a current flowing in a closed path. That is what a circuit is. We'll come back to it. So how is this electric current defined? It's nothing but the time rate, meaning how fast something is happening, at which the charge flows through a surface. That's what the current is. So we can say it is, say we stop at a certain place, I say an area, and look at the charges flowing, crossing this area. And let's say we wait for, say, 10 seconds, okay, and see how much charge flows per unit time or in a second. So this is what a current is, the rate of flow of charges. You take the charges divided by the time it took to through which that amount of charge flew through that, across that surface. It's called the average current. The symbol we use for current is I. Okay, so we are watching it over a period of time, so it is the average current. What about the units for the current? The unit for current is coulomb for charge and second for the time. So the unit for current, excuse me, please, you are in the class, please. You want to do the lecture, you can come down here and do it. Please settle down fast. We already started the class. So the current is how fast the charges flow. So it is delta Q divided by delta T. So Q, SI unit for measuring the charge is coulomb, and the time is in second. The unit for current will be coulomb per second. Please come to the front. One of you come to the front. Sama, come to the front. Yes, come to the front. Come to the front, please. Thank you. So coulomb per second is the unit for measuring the current, but as it happens, it has a single name, amperes. So amperes is the name for coulomb per second. It's again after a physicist who worked on the current, electricity. So to honor him, we call it amperes. The symbol is A. But you should remember it is actually coulomb per second. Now that was an average current. So as it happens like in the speed and velocity, we have the average velocity, average speed, then we define the instantaneous velocity and the instantaneous speed. So that's when we make this delta T, we make it as small as possible. Mathematically, we make it to go to infinitesimally small to approach zero. That is then we have the instantaneous current. So when you have a steady current, there's no difference between instantaneous current and the average value. SI unit is ampere. Okay, whether it is instantaneous current or the average current, it is the same unit. Right. We continue to look at this current microscopically and see what is happening. We know there are two types of charges, right? Positive charge and negative charge. So we can have current, electric current, either with the flow of a positive charge or negative charge. Okay, both going to be current. So now when the positive charges flow, we say that is the direction of the current also in the same direction as the flow of the charges. So look at the A here. The positive charges are flowing across this surface area A to the right. So the current direction is also to the right. But when negative charges flow, here we are showing it flowing to the left, but the direction of the current is not in the same direction as the charges flowing, but in the opposite direction. So please pay attention to that. So there is a difference because convention, convention means agreement. Okay, we scientists agree, they come together in a meeting, they say, okay, let's take the direction of the positive charge flow as the direction of the current. So that doesn't mean negative charges doesn't constitute current. It is a current. But you should remember, we flip the direction of the current to be opposite to the flow of the negative charges. But flow of the positive charges is the same as the direction of the current. It's a convention. Common conductors is something that allow the current to flow, electric current to flow, the charges to flow. Such as copper. Copper is an example of the most common conductor that we use. The current is due to the negative charge, the electrons. Because what is positive charge is the proton, right? Protons are bound to the nucleus of the atom. They are not free to move. If it is to move, they have to move with the atoms. You don't see the atoms flowing, right? That it will be molten. So it is only the free electrons in the metal or the conductors that is flowing. Electrons are negatively charged. So it is a common practice to refer to the moving charges as the mobile charge carrier. Okay, a charge carrier. But the charge carrier can be negative or positive. So commonly in a copper wire, it is the electrons, the negative charges are the charge carriers. But in a solution, ionic solution, we can have both positive charges flowing as well as the negative charges flowing. Okay, power. So we can carry energy when the charge is flowing. Okay, when the charge is flowing, as it moves, it can lose its potential energy. That's what happens. So that potential energy can be given to the electric bulb, for example, as light energy. So that's how we transfer electrical energy to some other forms of energy. So the positive charges move from high potential to region of low potential, it loses its energy. Potential energy decreases. But on the other hand, negative charges flow from low potential to high potential, but still it is moving to a lower potential energy. So you should know the difference. I'm calling potential and potential energy two different things. So in a circuit, what happens as the current flow, it loses its energy. So there's a change in the potential energy of charge, it is negative. But most of the time, we are interested only in the magnitude of the energy flow. It is what is desired. The power is now delivered to where? The lost energy, it is delivered to the circuit element. If there is a resistance, you will see the resistance heats up. It suppose is a wire inside the bulb. Not only it heats up, it even emits light. So that's a useful energy. Okay, so now we are looking at a wire, and this is a cross section, and we are looking at the positive charges flowing. Actually, in the wire, it is a negative charge which is flowing, but it's easy to look at the concentrate on the positive charge, because positive charge direction is the direction of the current flow, positive charge moving direction. Let's say we watch this guy for a period of delta t, a time of delta t. During that period, the charges would have moved, let's say, a distance of delta x. So we are trying to get an idea of the current, okay, how the current is related to the flow of charges. And let's say n, the small n, is the number of charge carriers per unit volume, like a density. How many charges we have in a unit volume, in a meter cube or centimeter cube, something. If n is the number of charge carriers per unit volume, if you multiply the n by the volume in this period of delta t, how much volume it has crossed, it will be area multiplied by delta x. So if I multiply the density by the volume, we will get the total number of charges, the total number of charges that is crossing this area. So for V, I can write delta x. So n into A delta x will give you the total number of charge carriers that is crossing that area in that period of time, say delta t. Now, if I multiply this NA delta x by the charge of one charge carrier, let's say it's Q. Say Q, let Q be the charge of one charge carrier. So what I'm getting now, this is the total number of charge carriers. You multiply by the charge per charge carrier, you are getting the charge, total amount of charge, because one charge carrier has Q amount of charge. So this is the total number of charge carriers that has Q into number of charge carriers will give you the total charge. So let me call it delta Q. So I wrote it here. Okay. Now I take this equation, divide this equation by the time interval through which we are watching it on both sides of the equation. So the equation is still correct. Now on the left-hand side, it becomes delta Q over delta T. I can combine that delta T on the other side with the delta X. So now you can recognize something. What is this? Delta Q over delta T. What is delta Q over delta T? Current. Okay. So this is the current. That's the definition of the current. And can you recognize this? The current is moving at distance of, the charges are moving at distance of delta x in a time of delta t, which is the speed. The definition of average speed is delta x over delta t. So this is the speed of the charge carriers. We are going to call it vd. I'll tell you what this d stands for. D stands for drift. Because you know the meaning of the word drift, drifting. Yeah, and just going slowly, okay, drifting. There is no aim, okay, but it is drifting, going here and there. That is drift, okay, right. So we have finally this equation, because delta Q over delta T is the I, and delta X over delta T is the drift speed. So as expected, the current has to be related to the speed of the charges, because the definition of the current is the flow of charges, right? So the I is proportional to the drift speed of the charge carriers. Yeah, okay. Yeah, in a metal, it is actually the negative charge which is flowing, not the positive charge. But for the purpose of illustration, I chose the positive charge. There are cases where the positive charges can flow, like in a liquid. You know, if you put two electrodes in a sodium chloride solution or something, the sodium ion will move toward the cathode, whatever, anode, cathode, those two electrodes, okay? So in a solution, you can have the flow of positive charges. It is not that, but in a wire, it is actually the electron which is moving. But I chose, I mean, this is, I am imagining, okay? It is not, of course, you are right, okay? It is there. But when the electron flows to the right, is actually, you can say the current is flowing in the opposite direction. That's the convention, okay? It's just for the illustration, that's all, okay? So I'm choosing the positive charge for the example here. Okay, so now the current and the speed of the charge carrier, it can be electron, it can be positive charges, doesn't matter. It is related by this equation. It is function of the density of the charge carriers, charge of a charge, the size of the charge or the value of the charge, multiplied by the cross-sectional area. It's also proportional to the cross-sectional area. Okay, if the conductor is isolated, okay, is somewhere, you know, not connected to any electric field, like connected to a battery, then the electron in this conductor, now we know it is the electron, which is a charge carrier in a common material, it moves randomly in all directions, because there is no reason for it to move in a particular direction. So when one, let's say, let me draw it. If one electron is moving this way, there'll be another electron moving in the other direction. So on average, there is no motion. Every right side is cancelled by another left side one. So on random, there are, you know, no preferred direction of motion. There is no motion at all. I mean, there is no more. Electrons will be going here and there, but not necessarily in a certain direction. But the moment I connect a battery, that will set up an electric force inside this electric field inside these wires. Now they will experience a force. The electron will have a force in the opposite direction to the electric field because it's a negative particle. So then we have a preferred direction for the charges to move. So here we are showing a negative charge, say an electron, in an electric field, let's say to the left. So it will have a force that will make it to go in the right direction, because you know the electric force is charge multiplied by the electric field. So if Q is negative, the direction of the electric force will be opposite to the direction of the electric field. So electric field is to the left and the electron is experiencing a force to the right. But we have atoms. Okay, so as the electron charges are moving, the electrons are moving, it is going to hit these obstruction. The atoms are on its way, maybe another electron as well. So every time it has a collision, its path will change. So when it hits something here, it will move this way. Maybe another one, it will move that way, this way, that way. It will keep zigzagging like this. But somehow it wants to go to the right. So it will end up further down right. Yeah. No, it is now not random. It wants to go to the right. It is feeling a force to the right. But as it is going to collide with obstructions, blocks. So every time it hits, it will be reflected in the opposite direction, whatever the because it is not allowing it. So it comes like that. It will be going like that. Every collision, its path will be changed. But again, it wants to go to the right because it's feeling a force to the right. So it will slow down its progress. Okay, so that's why the drift velocity of these charge carriers in a medium is very small. Okay, it's like millimeters per second. So in a second, it will move less than a millimeter, actually, fraction of a millimeter. Yeah. Okay, so it's very slow. So that's why we call it drift speed. Okay, the net drift speed is small. Even when you connect it to an electric field by connecting a battery, the current will be moved. The charges will be moving with a slow speed, but it will be moving. So that's why it will lose its energy along its way and give the energy to the circuit elements. Then we will have some useful energy utilizing those energy. Okay. Right. So we are going to look at a simulation of the current or the charge flow by clicking on this link. I have already opened it. So let me go there. Did I open it? Maybe I didn't. I thought I opened it. Oh, okay. Okay. So let me click that. It will take some time to open. Here we have a electric lab, okay, where we can connect a circuit. Let me and do some experiment. Okay, so these are my toolkits. I'll grab a battery and put it there on my bench and take some wires, connect it to the battery. Another wire, connect it. I will bend it. Look nice, okay. So then I take a bulb, connect it, and let me take another wire, connect it there, and I will move the other end of the, the plus minus side, okay, so battery. So I take another wire and, okay, maybe one more wire, another wire. I need a switch, okay, I need a switch, got it? There is a switch here. Always you need a switch because you don't want to keep the current flowing, okay? You should be able to control it by opening the switch and closing the switch, right? Okay, one more piece of wire. Right, the circuit is complete. What you see as the negative sign all along the wire is our charge carrier, could be an electron, okay? So now there is no current because there will be random motion, but no electric field inside because electric field is from the battery, right? The battery has charge separation, so there is an electric field at the battery. But it is not going through this wire until I close the switch. The moment I close the switch, what you would expect, the electron here, okay, there is an electron at the battery, inside the battery, it's ready to go. This electron will move around the circuit, right? So when you close the switch, what do you think? How long it will take for the bulb to light up? It will be immediate, okay, very quick, or it will be slow. It will take, say, seconds, or second is very big time. But it is not what happened, right? The moment you put the switch, the bulb comes up immediately, almost immediately. Why? Yeah, but I said the speed of this electron is very small. It will take time for this electron to come to the bulb. There is collision, yeah. Yeah, right, yeah. So what, even at the bulb, the bulb will lit up if the electrons are flowing in the bulb. So the moment you close the switch, what happened? The electric field from the battery will move at the speed of, not the electrons, the electric field from the battery will be transmitted to the bulb location at the speed of light. Okay, it's a wave, electromagnetic wave. So the electromagnetic wave or the electric field will immediately be present here, not immediately at the speed of light. Okay, so the electron will feel the electric field the moment, quickly, immediately after you close the switch, the electric field will travel to this place at the speed of light. So it will feel the electric force, so it will move. So that means the light will be lit. Okay, let me close the switch. Oops. What happened to my circuit? Oh, do I have to do it again? I'm sorry. Yes. Okay, I don't know. I see, it doesn't take that long. Okay, wire, battery, wire, bulb, wire, switch, wire. Okay, one more wire, just to make it look nice. Okay, right, close the switch. It's immediately lights up, open the switch. So you know what happened, electrons are all over the wire. The moment you close the switch, the electric field is felt on each of these electrons, wherever it is in the wire. It will travel at the speed of light. You know what is the speed of light? That's the maximum speed we can have. Anyone knows the speed of light? Yes? 10 to the power 8. It's like 300 million meters in a second, 300 million meters. So it's almost immediate, right? I mean, this is nothing for that speed. Which one is it? Oh, okay. Right. So we looked at this simulation, which showed you that in an electric circuit, it is the electric field which is traveling through the wire, the speed of light. So when you put the switch on, it comes on almost immediately. Okay, let me take attendance, then I will continue. Could you be quiet, please? Excuse me. Okay, the three of you, there on the left side, last row, come to the front, please. Come to the front now. Come to the front now. Yes. All the way to the front, the first row. I'm waiting, hurry up, please. Where is she? Sit down, please. So the drift speed is very small. So you understand why it is small? Because it's going to have collision on its way. That's why it's small. But it doesn't matter to us because we don't have to wait till the electrons to move around the circuit to get the energy. So what happens is when you turn the switch on, immediately the electric field is felt everywhere. So it travels at the speed of light and you get the light, bulb lighting up almost immediately. The speed of the electrons, the drift speed is very small, like in millimeters per second or even less. But whereas the speed of the electric field is almost the speed of the light. What is a circuit? We talk about electric circuit. Circuit is a closed path where, like what we set up there, we have a circular, not necessarily circular, a closed path. When you close the switch, it becomes a closed path where the current can travel starting from the battery and come back to the battery. We can use what is called a circuit diagram to represent the circuit. Now, in a circuit, we have some quantities that are of interest to us. It is called the current, that's what we know, and the potential difference. We should be able to measure them to understand the circuit here. Yeah. Yeah. Yes, yes. When you close a circuit, the light bulb blows up. That's because suppose for some reason you get a bigger current flowing than expected. The current when that flows through the circuit element, it can heat up. So it loses the energy. So sometimes the losing of the energy will become it start heating up the atoms, okay, vibrate more faster. So when it heats up, it burns. Okay. That's the reason. The electrical energy converted to thermal energy, then it burns, then the circuit becomes disconnected and the current stops, but the damage is done. It depends on the battery, but if you sometimes unexpectedly, the battery voltage can become high for some reason. Okay, then not battery voltage doesn't change, but for example, there can be many reasons why the current all of us unexpectedly can go up and then blew up the. That's why we have some protection mechanism like fuse. So fuse is a thin wire, okay, small wire. So when it is a larger current than expected flows through that fuse, the fuse burns and it becomes an open circuit and the current will be stopped and it will not damage the other elements which it is protecting. Yeah, the circuit is not a circuit anymore because it's become open. Okay, the current cannot flow. Like a switch, yes, more or less like a switch. But you have to manually replace the fuse to let the function again. What is a circuit diagram? It's something that we represent the real circuit in a diagram. So I will show you. Here, it's not a circuit diagram, it's just showing the circuit like we set up there. We have a battery and some wires. Now we said we should be able to measure certain qualities of interest. These are the current and the potential difference. So someone wants to know if there is the bulb, what is the current through that bulb? So we can simply connect a device called ammeter. Ampere meter. Ampere is the unit for measuring the current. So with an ammeter, you measure the current. So that's why we call it ammeter. So whatever the current that flows through the bulb will flow through the ammeter. So what the ammeter is measuring is the current through the bulb. So ammeter must be connected in series with the bulb. So you will measure the same current that flows through the bulb will flow through the ammeter also. So ammeter will be correctly reading the current through the bulb. Okay, this is voltmeter. So as the name implies, it will measure the voltage, voltmeter. Now see how the voltmeter is connected. It connected in parallel to the bulb. We want to measure the potential difference across the bulb. So you connect it like that. So it will measure the potential difference across the bulb. So you see the difference? The ammeter is connected in series with the element to measure the current through that element, but the voltmeter is connected across the bulb to measure the potential difference across the bulb. Okay, so this is the real circuit, but we can draw a circuit diagram. What we mean by circuit diagram is to represent this element by symbols and the wires by the line. The battery, this is how we represent the battery, a short line and a long line. Short line is the negative side of the battery and the long line is the positive side of the battery. So we got the battery here. And then the bulb is, this is how the bulb is represented, a circle and the wire inside. An ammeter is a circle and you put the letter A, so we know it is an ammeter. Voltmeter is a circle and the letter V. Now this is the circuit diagram. So we represent the real element by symbols that represents the real element, and for the wire we draw lines. So it's a circuit. What is missing here? The switch, right? Should I put the switch? Switch circuit is the symbol for switch is like this. Okay. So there's a gap. So you close the switch, the circuit becomes complete. Closed. I'm sorry. Fuse. I forgot. Okay. Probably, no, I forgot. I really don't know. Sorry. Look it up, maybe Google it and see. Yeah. Usually it doesn't come in a practical circuit. Okay, so voltmeter is used to measure the voltage, the potential difference, also called voltage, and that is connected in parallel. Okay, now comes a law that is used in electric circuit called the Ohm's law. Ohm's law. It's a person called George Ohm. He is in this period. He formulated the concept of resistance. Resistance to the flow of current. Okay, that's why it's called resistance. He discovered there is a linear relationship between the current and the voltage. You take a piece of wire and connect it to a battery. So you apply a 10-volt battery, there will be a certain current. You double the voltage, say 20 volt, the current will double. So he discovered that. So he saw that there is a proportionality between current and voltage. So he expressed that. He said that the current, or let's say the voltage, is proportional to the current. The proportionality constant, we call it R. So that is the resistance. Now, why that name resistance? I can explain it easily. Suppose we have two wires, okay, and we apply the same voltage to both of these wires, say 10 volt, for example. 10 volt to both of these wires. Maybe the wire 1, say this is wire 1, this is wire 2. Wire 1, the current is, say, 10 amperes. But wire 2, the current is only 5 amperes. Why? You can say wire 2 has more resistance. Yeah, it doesn't allow so much charge to go. So wire 2, because the current is less, that means it has more resistance. Wire 1, the current is more, that means relatively it has smaller resistance. So that's what is happening here. For the same voltage, if the current is small, the resistance is high. If the current is big, the resistance is low. So the name resistance is appropriate for this R. R tells you how much resistance that material that is present to the flow of the current. So resistance, the symbol is R. What about the units? It is volt per ampere, right? This is volt, this is ampere. So the unit, SI unit will be volt per ampere. And we have a signal name for volt per ampere. It is called ohms. This is the Greek letter omega, right? This is a Greek letter omega. So, but it is, we don't say omega, we say ohms, because after this physicist who worked on this, his law, the Ohm's law, so we call it ohms. It's a bit confusing. It is really the Greek letter omega, right? It is omega. Greek letter, yeah, omega, but we call it ohms, okay? We don't call it omega. And, you know, this is also omega. Maybe you have seen in mechanics, angular velocity. This is omega, this is also omega. Why there are two omegas? It's like this. What is this? A. What is this? A. Same thing. It is the uppercase omega in the Greek alphabet. This is the lowercase omega in the Greek alphabet. Right. So now, why do we have the resistance and different resistance for different material? Resistance is because of the resistance, I mean, the obstruction. When the current flow, that means there's a charge flowing, right? It is going to see other atom, fixed atom. So it is going to collide. So it will resist the motion of the charges. So that means current will be restricted. So that is why we have the resistance. Resistance in a circuit arises due to collision between electrons carrying the current between the electron as well as the fixed atoms inside the conductor. Experiments show that for many material, this law, the Ohm's law, is obeyed, okay? But not all of them. Although we call it a law, it is not a law because it doesn't apply universally to everything. Certain material obey this law. So anyway, it became known as Ohm's law. We are stuck with that. It's not proper to call it a law because law means it has to apply equally to everything, right? But it doesn't. But we just keep calling it Ohm's law. It's actually an empirical experimental relationship that is valid only for certain material. Any material that obey the Ohm's law, we call it ohmic material, ohmic. But there are things that are not ohmic. So here is a graph of volt potential current against the potential difference, current versus voltage. And you can see the slope of, because this is one that is obeying the Ohm's law. You can see when the voltage is double, the current is double. It's straight line. That means it is obeying the Ohm's law. Okay. The slope will be 1 over R because remember the relationship is like this. But I put in the y-axis, I put the current, and in the x-axis, I put the potential difference. So the slope will be not R, but it will be 1 over R. Right, now here another graph. It's not a straight line, so it is not an ohmic device. It is a non-ohmic device. So usually semiconductors, okay, which are not conductors between insulator and conductor, they show something like this. They don't have a straight line. So the resistance changes, okay, it is not, we don't have a constant value for resistance. It's non-linear, the voltage, current voltage relationship is non-linear. An example is a diode. It's a very important element, circuit element in electronic, diode. It's a non-ohmic device. Now we're going to introduce what is called resistivity. It's not the same as resistance. It's related to the resistance. Suppose we have a material, let's say copper, okay, made of copper, say certain length L, and another material, different length, say double the length, some different length. Same copper, this is also copper, both of them are copper. If you measure the resistance of these two, they will have different resistance. It actually, the resistance is proportional to the length. If you double the length, the resistance will double. And we can do something. We keep the same length and make it thick. What do you think the resistance will become? Decrease. Because it has more area for the charges to flow. Okay? The charges now going through a bigger area. So it can cross that area. More of them can cross. Okay, not easy. More of them come cross at the same time compared to the thin one. So the resistance will decrease. So the resistance is linearly proportional to the length. Length increases, the resistance will increase, but inversely proportional to the area. When the area increase, the resistance will decrease. Okay, so this is, and then the proportionality constant there is called the resistivity of the material. We use the symbol, again, a Greek letter. This is a Greek letter. It is RHO, rho, like omega. It's a Greek letter again. For some reason, we use Greek letters for this. Yeah, because you know, we need a different language as a English. We need a different language for this, so they don't confuse with the English alphabet. So yeah, maybe I don't know what the reason is scientific. Maybe because those. Anyway, never mind. We don't care, but we are stuck with that. So, this is resistivity. It is rho. Okay, it is not P. P is this. This is a Greek letter rho. So it is called the resistivity. It's not the same as resistance. Resistivity is a constant for a given material. So copper has a specific value for its resistivity. Okay. So copper has a certain resistivity. All right. Let's do this question on resistance and resistivity. Calculate the resistance per unit length of a 22 gauge nichrome wire of radius this much. So we have certain nichrome wire. So the material is fixed. That means it has a constant value for its resistivity. And the resistivity of nichrome is given to us. Oh, what about the unit for resistivity? I didn't discuss. I should have done that. See, resistivity, I can write like this. Resistance is ohms, area is meter squared, and length is m. So you can see the SI unit for resistivity will be ohm meters, ohm meter. SI unit for resistivity is ohm meter. So let's calculate the resistance per unit length. Okay, resistance is given by this equation. If I know the resistivity, the area and the length, I can find the resistance. The area we can find because radius is given. So we in wire mean what kind of cross section a wire has? Circle. If you cut the wire, the cross section is a circle. So what we need here is the cross sectional area of a circle. You know, circle, what is the area of a circle? Anyone know the area of, yeah. Pi r squared? Pi r squared, no, pi r squared. This is the area of the circle. So we know r, 0.321 millimeter. So I can get the area. Resistivity is given. What about the length? He wants not the resistance, but he wants the resistance per unit length. So we don't need, he's asking for R divided by L, not for R. So I can just, so I can substitute for this and the radius, and I can calculate the resistance per unit. Let me call it X, okay? I don't want to get the number. Let's say I found it and I have completed part A. I found the resistance per unit length. So let me go to part B. Part B, if a potential difference of 10 volt is maintained across the 1 meter length of the nichrome wire, what is the current in the wire? So now we have to apply the Ohm's law. If we know the potential difference and if we know the resistance, I can find the current. He's asking for us to find the current. Okay, so let's find the current. So I is equal to delta V over R. We have delta V is telling 10 volt, substitute, and he wants the resistance. Well, in part A, we found the resistance. We found the resistance per unit length, right? But here he is giving the length. It's 1 meter. So it is the same thing. We found the resistance per unit length, and then now the length is 1 meter. So it is the same. Whatever the answer we got for A is the resistance. Okay, I calling it X. So we found. So we completed part B also. Okay, so let's go to part C. The wire is melted down and recast with twice its original length. Find the new resistance Rn as a multiple of old resistance. Okay, let me explain that. We have this wire, okay. Let's say it has a certain area and a certain length. Let me call it L1 and A1. We take this wire and we stretch it or melt it and reform this. When you reform with the long, twice the length. Now, what do you think will happen when you make it twice the length? Okay. What will happen to the area? It's going to become thinner, right? Because we are stretching it. I mean, we are making double the length. Okay. Now, can you relate A2 and A1? Half the thing, because length is doubled. Yeah, A will be halved actually. How do I know it is exactly halved? Can you prove it? Yeah. Yeah, can you prove it mathematically? Twice its length. Yeah. Okay. Yeah, okay, I understand, but can you convince it mathematically? I mean, okay, now what I mean is, what is constant here and here? No, I mean, this wire and this wire, it is the same wire, right? The amount is the same, right? The volume of this wire is the same as the volume of this. Can you agree? Volume is the same. So volume is A1L1 here. The volume is A2L2 here. So A1L1 must be equal to A2L2. Okay, that gives you our answer. So A1L1 is equal to A2L2. Volume is cross-sectional area multiplied by the length, right? So AL. So this gives me A2 is equal to L1 divided by L2 multiplied by A1. L1 divided by L2 is half, because L2 is twice L1. So this gives me the new area is half times the old area. Well, that's not what we want. I want the resistance. Now let me go to the resistance. The new resistance expressed in terms of the old resistance. Resistance is rho L over A. So new resistance R2 will be equal to L2 divided by A2. L2 is 2 times L1 and A2 is A1 divided by 2. See what happened now? 2, when it comes up, it will be multiplication. So it will be 4 rho L1 divided by A1. This is the old resistance. Okay, so because what we did now, the resistance, new resistance will be 4 times the old resistance. Okay, right. So I'll take up this, then we will stop. Okay, give me 5 minutes more, or 2 minutes more maybe. Now this is another section, temperature variation of resistivity. Although we say the resistance for a metal, which is an ohmic device, but however, if the temperature increases, the resistance will change. So there's a temperature variation of resistivity and the resistance. For most metals, the resistivity increases with increasing temperature. Okay. So sometimes it is useful for us. We can use it to measure the temperature. Because if it's proportionally changing, all you have to do is to get the resistance and we can calibrate it to measure the temperature. We have thermocouples and things like that. Not thermocouple, to measure the temperature from the variation in the temperature, in the resistance. So why does it happen? When the temperature increases, the atoms, okay, they vibrate more. So it will present a more obstruction for the flow of charges. So we can kind of understand why the temperature will increase the resistivity. Therefore, the electron find it more difficult to cross. Electrons are the charge carriers. So this is the equation, the variation of the resistivity with the temperature. The resistivity at a certain temperature T will increase proportionally, and this is the proportionality constant. We call this temperature coefficient of resistivity. What are these rho 0 and T0? This is the resistivity at some reference temperature. Okay, so suppose we know the resistivity at some reference temperature T0, we can get the resistivity at some other temperature if we know the coefficient of temperature coefficient of resistivity. So we will use this equation to do calculations. And here, instead of resistivity, we can write the equation in terms of resistance as well. This is what we had in the previous slide. Now this is what happened. Instead of rho, I can write it as, because you know R and rho are related like this. Okay, for a given material. So if you write this, R is equal to rho L over A here, and for R0, rho L rho naught L over A. L over A cancel with L over A, so we get the relationship. So it's the other way around. R is equal to, yeah, okay, R is equal to rho L over A. So here we write rho. No, from here we need to go that way. So this is what we wrote first. So if R is equal to rho L over A, rho is equal to A R over L. A L cancel both sides, so we have the relationship for the resistance R as well. Okay, I think I will stop now because the new section. So, okay, let me end.